much, Richard. And I wanted to go ahead and just say thank you to the organizers for inviting me. I'm sorry I could not be there. My fiance just recently had knee surgery, so I'm playing caretaker and nurse. So this is work that's ongoing with my collaborators in Germany and at Lawrence Livermore on how we're using a old tool, but now a recent tool, a newly discovered tool, using quantum hydrodynamics to investigate warm dense matter, and some interesting discoveries we've made on what shocks do in a quantum hydrodynamics description. So the work that you're going to see today is based on a paper we published a year or two ago in Contributions to Plasma Physics. And a lot of the details in that that you'll hear today are actually in that paper. So when we talk about high energy density physics, it's really a description. It's a category of matter at extreme conditions, and it spans a wide range of density and temperature states. So typically what we talk about in terms of classifying warm dense matter, or actually high energy density physics states, is matter or phenomena beyond a megabar. So you can think of that pressure megabar is equivalent to an energy density of about an electron volt per cubic angstrom. And an electron volt, just so in case you're not used to using those types of terms, is equivalent to about 10,000 degrees Kelvin. So we use electron volts and KeV, kilo electron volts, quite frequently. So it spans everything from planetary interiors to inertial confinement fusion, if you think of the recent ignition experiments, and also a magnetic fusion. If you look at the trajectory here's an example of the trajectory of the gas region in inertial confinement fusion capsule, it actually spans those regions. It starts on the left and goes to the right in about tens of nanoseconds, and it spans the warm dense matter to the hot dense matter regime. And that's, in fact, how we classify the phenomena. And I'll describe more about what the warm dense matter means in more detail. But qualitatively, we're looking at, in warm dense matter, we have states where the electrons are degenerate. The plasma can be strongly coupled. And it's a very interesting area that's at a cross-section between classical plasma physics and condensed matter physics. It doesn't fit in either camp. It's non-ideal plasma physics, and it's hot condensed matter physics. So it's this very interesting area where you have strong correlations and you have degenerate electrons. And so one of the ways that I like to look at the state of warm dense matter is if I look at this plot again, sorry for going back, and let's look just at the densities of 10 to the 24 and look at some of the properties of warm dense matter as we span temperature but keep the density at 10 to the 24. Well, here's a plot where the vertical axis represents some sort of going from an ideal state to a non-ideal state. And here's where the electrons exhibit partial degeneracy in the warm dense matter regime. So temperature is on the horizontal scale. And so temperature goes from about 10 eV to about a kilovolt. And so what I've plotted on the left-hand side on the vertical scale is the ratio of the Fermi energy to the thermal energy. And when that is greater than 1, or on the order of 1, you have electron degeneracy. And so you see that, in fact, as the temperature increases, the degeneracy factor goes closer and closer to classical Maxwellian statistics. And so what I've put in shaded blue and the arrows is roughly what we would define as warm dense matter. So this is what I was saying earlier about degenerate electrons. Now, that's just one aspect of quantum mechanics. So we think of degeneracy when we talk about quantum mechanical behavior of matter, we think of degeneracy, but there's also quantum non-locality. And quantum non-locality refers to the spreading of the wave packet. And here we can form a dimensionless quantity, which is the ratio of the thermal de Broglie wavelength to the Landau length. So the Landau length, this is particularly used, these quantities are used particularly when we're talking about scattering processes. For example, electron-electron, or in this case, electron-carbon or carbon-carbon. So the Landau length is the sets the length scale at which the mean kinetic energy is equal to the mean potential energy. The lambda sub E is the thermal de Broglie wavelength. And for Boltzmann statistics, it goes as H over the square root of 2mkt, just as you've seen in the textbooks. But for degenerate matter, the temperature should go to the Fermi temperature, where the statistics are Fermi statistics. And this is what we see, that in fact, what's surprising, for example, if you look at electron-electron or equivalently electron-proton scattering, in fact, the ratio of the thermal de Broglie wavelength to the Landau length grows. And this is because at high temperatures, the wave packet spreading becomes more and more important. But then you see, for example, I'll just jump down to carbon-carbon. You see that, in fact, the scattering process there is purely classical. So when we're talking about scattering processes, the dominant length scale for electron, proton is actually the thermal de Broglie wavelength. Whereas for processes like carbon to carbon, it's actually the Landau length, classical Landau length. And if we do simulations, for example, in hydrocodes where we have to have Fokker-Planck equations, this appears, if any of you know anything about the Coulomb logarithm, this is the small length scale that appears in the Coulomb logarithm. And then finally, the last thing we focus on is the Ichimaro coupling parameter. And this is the ratio of the potential energy to the kinetic energy, and it's inversely proportional to the number of particles in a Debye sphere. And this tells us how ideal our plasma is. So we can see that, in fact, if I look at ion and ion collisions or ion-ion coupling, that in fact it is pretty non-ideal. And this is principally because of the ionization state, Z. Whereas gamma EE, the plasma coupling parameter for electrons, tends to be ideal. All right, so we see that it's an interesting mixture. We look an interesting mixture of physical phenomena in the warm dense matter regime, where the electrons behave as an ideal plasma, but they're degenerate. But the ions can be strongly coupled. So this is a very interesting mixture of states. So particularly challenging for warm dense matter is the theoretical description of this non-ideal warm dense matter regime. And so some of the characteristics, just to summarize, are diffraction or quantum non-locality, Fermi statistics. There's strong correlations, particularly between ions and ions, and we can have finite temperature effects also. So what are some of the tools we've used in the past? Well, for equilibrium phenomenon, density functional theory. For dynamics, things like time-dependent density functional theory. There's also molecular dynamics. So molecular dynamics with quantum statistical potentials has been within the last decade, has been applied to both warm dense matter and hot dense matter. Quantum Monte Carlo, and then kinetic equations also, which we've heard about yesterday and today. But the other tool is the one I want to introduce to you today, which is quantum hydrodynamics. And quantum hydrodynamics really, in some sense, is in some sense part of a hierarchical description of matter. And in this case, it goes from the atomistic through the statistical to hydrodynamics. And this is classically, for example, we would go from something like the Liouville equation to something like a Boltzmann equation to classical hydrodynamics. Well, there's an analogous hierarchy in quantum mechanics, of course. There's the atomistic, where we have n-particle wave functions. There's the statistical, where we can formulate quantum mechanics in terms of the Wigner equation, or quantum Leonard-Bolescu, or quantum Boltzmann equation. And then there's something I'm going to introduce to you next, which is the hydrodynamic description, where in fact the material can be described, the quantum plasma or quantum material can be described completely in terms of the field variables of number density, velocity, and energy. And so what's the advantage of this type of approach, and it's no different than the advantages of hydrodynamics for classical plasmas, is that with hydrodynamics, you can operate at longer time scales and larger length scales. So if we want to look at dynamical systems on larger time scales and length scales, hydrodynamics and certainly quantum hydrodynamics holds a lot of potential. So let me just remind you, even though we saw some of this yesterday, what the equations for the hydrodynamic equations look like for plasmas. So the top equation is the continuity equation, which represents conservation of mass. S here, the subscript, just represents species. There's also a conservation of momentum. I'm going to here fill this in. We have an equation state, which is a pressure. We have a Hartree or mean field Coulomb term. And there's collisional integrals, which represent some sort of momentum transfer between different species. And that can be between different species of ions, between ions and electrons. And that whole right-hand side, of course, can be written as some divergence of some energy functional formally. And there's also a Poisson equation. So here we're just talking about electrostatics. We're not going to introduce magnetic fields, but there's no reason why we couldn't. But for this talk, we're just going to focus on electrostatics. So quantum hydrodynamics actually emerged in a very interesting period. It emerged shortly after the invention of quantum mechanics, and Madelung, who you see there, wrote published a paper. And if you can't read German, you can probably sound out that it says quantum theory in hydrodynamic form, where he introduced density and velocity fields by it being a set of hydrodynamic equations that was completely consistent with a single particle Schrodinger equation. Some 5 years after that, Wigner introduced the phase-space distribution function, which obeys a kinetic or transport-like equation. It's non-local, and that's an important aspect because that's the features of quantum mechanics that have to be included. And also this phase-space distribution function is non-negative, and that's a characteristic of the Wigner equation. So let's look at, here's a quantum hydrodynamic primer. So let's start off with the Schrodinger equation, and let's just make an ansatz for the solution, which is some amplitude R, capital R, and then an exponential of a phase factor. And you take that ansatz and you just substitute it into the Schrodinger equation. What you get are a couple set of equations. It looks a little reminiscent. The first equation looks a little reminiscent of the Hamilton-Jacobi equations. But if you take that and you identify the gradient of the phase factor with a momentum field, and then the absolute square of the amplitude with a number density, you get a set of equations that look just like a set of hydrodynamic equations. And so you have your advection terms, you have a continuity equation, you have a momentum equation, you have something that looks like a gradient of a pressure, and you have something that looks like a gradient of an external potential. Now that pressure term is interesting because it has this very strange functional form, but what it represents is quantum non-locality. It represents the fact that the wave packet is actually spreading, and it's interpreted here as some type of Bohm pressure. So Bohm is the person in 1954 that also worked in reformulating quantum hydrodynamics this way. So a caveat here is that everything we've talked about is for single particle quantum mechanics. It should not be extended as is to many particle systems like plasmas. And you will find in the literature for the last 30 years, people are doing that, where they will take this set of equations and just apply it directly. And so you have to be careful. So buyer beware. So let's look at this in a little bit more detail and see what's wrong with this equation. Well, let's focus on the momentum equation. The continuity equation looks fine. Well, there really is no equation of state. There's no particle-particle interactions. There's no quantum statistics. And there's no energy equation. And I'm going to address the energy equation problem at the end. But the gradient of a potential is an external potential. It's not an inner particle potential. And again, the pressure term is due to wave packet spreading. It's not due to some sort of equation of state due to a collection of particles. So the extension of quantum hydrodynamics to many body systems really has its foundations with three individuals. There is a wave function ansatz for many body quantum systems, and I'll show you an example of that next, where you can take the ansatz approach and incorporate quantum statistics and anti-symmetrization for fermions and go through the same process. There's a phenomenological fluid approach done by Felix Bloch, where he said, you know, what the heck, I'm just going to assume I already know I have a Thomas Fermi equation state. I may have a Kurtznitz term for gradient corrections, but I'm just going to say that's my equilibrium state. And I'm going to have a phenomenological model that says, okay, my non-equilibrium is going to be described by a set of fluid equations, and all that stuff with the equation state is going to be on the right-hand side. And I'm going to elevate this to a dynamical state. So I'm going to say I'm going to be able to evaluate dynamical properties of a quantum mechanical system using this approach. And then there's the approach that I think has a lot of potential, but just has not been explored very much, which is to use the Wigner equation and taking moments of the Wigner equation. So this is just a single particle Wigner equation with a non-locality, but you need to extend this Wigner equation to many particle systems and take moments. And you can do that with second quantization. I won't go, I have a whole other talk on that, but you can then extend the Wigner approach to include many particle systems. So all of these lead to a set of hydrodynamic equations depending on density and velocity fields that contain some sort of pressure term. It could be a Thomas Fermi pressure, quantum non-locality, correlations, and exchange forces. So here's an example of the Madeline approach from my student, who's now a postdoc at the University of Rochester, where he took the ansatz that Madeline proposed and made sure that there was proper anti-symmetrization and it would obey the Fermi statistics. And he basically just took that ansatz and stuck it into the many particle Schrodinger equation. And sure enough, he got a set of hydrodynamic equations, but with the proper right-hand side. He got a Thomas Fermi pressure. He got the Bohm pressure term, which is the quantum non-locality. He also got an exchange energy, exchange term, which comes from the fact that the wave function is antisymmetric. And he had Coulombic interactions also, so you get the particle-particle interactions. So this now starts to look like something we want to focus on when we apply quantum hydrodynamics to plasmas. And so just summarizing what these equations would look like if we included ions, we'd have a continuity equation, we have a Poisson equation, we'd have a momentum equation for the ions, and then we'd have an electron, what I would call a quantum hydrodynamic equation that includes Thomas Fermi pressure, that's due to degeneracy. We'd have an exchange term, this simple form is due to Dirac, due to wave function anti-symmetrization. And you have quantum non-locality, which is the standard Bohm term. And so this would be a set of equations that we are going to now use to apply to hydrodynamic systems. Let me just say that you can look at the properties of these plasmas by looking at just linearizing them and looking at small perturbations and looking at the response. So if we take the ion equation that I just wrote down and perturb that and looked at the response function, we in fact get a dispersion relation. And in the static limit where omega squared is 0, you get in fact the classical Yukawa screening due to the electron cloud being screened by the ions being screened by the electron cloud. Now, if we do the same thing for the electron QHD equation, we get the following dispersion relation. If we now look at the static limit of omega squared equals 0, we also get a screening, but now we get the so-called Thomas Fermi screening, which is appropriate for degenerate plasmas, and we get a correction due to Bohm, which can produce oscillations in the screening length, which is interesting, which might give us some sort of sense of experimentally observing these types of things. So now I'm going to wrap up the last 5-ish minutes and talk about applying this to shocks. And with this set of equations, and certainly with the interesting form of the Bohm pressure, this funny functional form, it got me thinking about, hey, is there interesting physical phenomena in hydrodynamics that we can look at anew, particularly applying to quantum plasmas? This has already been looked at for Rayleigh-Taylor instability, and then recently we've applied it to 1D shocks. And so what we're going to do is take our equations, and you will see, in fact, I'm going to simplify. We're going to take a simple model, and we're going to remove the Poisson piece, and we're going to remove the ion piece. So we're just going to look at an electron gas. All right, so this is just a simple mathematical model to help elucidate what the effects of this Bohm pressure would be on shocks. So that's the PQ. And what we're going to do is we're going to use the Miranda code to do this. So the Miranda code is a multi-species rad hydro code. It uses AMR. It has radiation, both gray and multi-group. It has, of course, hydrodynamics and MHD. And so we've modified this code to add in these modifications due to quantum hydrodynamics. And this is the result I'm going to show you, which is we start looking at the SOD shock tube problem. And in the upper left box, what I show is the initial condition, high density, on the right-hand side, low density on the left-hand side. And I've plotted with dimensionless scale, so all the distances are in relation to the Wigner-Seitz radius. And then we let it go. So without the Bohm term, you see the box on the lower left-hand side, you get the typical shock formation that you would expect, okay? But notice what happens when you turn on the Bohm term. Because of this funny cubic derivative, it induces in some sense, a non-trivial perturbation into the shock front. And so what I've plotted there is the initial condition of density on the middle box, density in green, the Thomas Fermi pressure in red, the exchange pressure term in blue, and then the Bohm term. And this funny cubic derivative causes this non-monotonic perturbation for the hydrodynamic equations. And what that does is it sends a ripple, no pun intended, into the shock front. It in fact both smears out the shock front and induces oscillations in the electronic density as the shock is evolving. And then that continues and gets worse and worse. So it's a feedback mechanism. So you'll notice that it induces this type of ripple into the density. That, in fact, then goes back and causes more ripples in the Bohm pressure term, and then feeds back into the density. So there's this feedback loop that goes back and forth. Now, this is for a gamma. This is for a very non-ideal, strongly coupled plasma of 2.7. I will tell you that I just don't have time to show you for a lower gamma that, in fact, this is a much less important effect. So this is more important for strongly coupled plasmas. So I'm going to rush through this part, but what I want to do is just point out that where that smearing comes from is if you look at the gradient of the Bohm potential at t = 0, this is the form of that force term, and that's what gives rise to this non-monotonic purple curve that you see there that perturbs the shock front. I won't have time, unfortunately, to look at, but what we've done is used Ryatov's paper to look at collisional and collisionless shocks and the formation and structure of shocks, and applied it to QHD. Let me just quickly go here and show you that let me just focus on the right-hand side, that figure. That is doing a perturbation expansion of the density and velocity for the QHD equations, and keeping quadratic terms in the density perturbation. And in fact, you do see the ripples. And this is that delta Q is the perturbation in the Bohm potential. And all that, of course, is proportional to h bar squared. So the ripples, to me, look to be a physical manifestation of this quantum non-locality. So my last slide is discussing, okay, now that was a simple problem. How do we extend this to ions? And so this is something that we just done. The challenge, of course, in any type of simulation is that the ionic timescales are very different than the electron timescales. So what we've done is just reformulated the equations so that we're going to focus on ionic timescales, not the electron timescales. And we're going to take assume the electrons in some sort of quasi-static or quasi-equilibrium, similar to the Born-Oppenheimer approximation that one uses in quantum electrodynamics. When we do that, we can say that the gradient of the potential is approximately equal to the pressure terms, and we just take that and substitute it into the ion equation. And what you get then is a single equation for the ions that depends on the ion pressure, and then the sum of the pressures for the electrons exchange and Bohm. Now, I've written the factors in an unusual way, and I've done that on purpose. And if you see that ME over MI, which is will be a small number, and you compare that to the way that term appears in the top electron equation, we are expecting that this means that for ions at least, the effects that we're seeing are going to be reduced by the ratio of the electron mass to the ion mass, but that's TBD. So we're doing the simulations using Miranda. So this is my conclusion. Two observations we made is that quantum non-locality via the Bohm pressure is the mechanism for generating electron density oscillations. And it's also the mechanism for smearing of the interface. The question is are the density oscillations interface smearing experimentally observable? So there is a parameter, which is a quantum diffraction parameter in QHD. I just didn't have time to show it. But when that quantum diffraction parameter is about 1, that's when we expect to see these type of oscillations. And those length scales are on the order of angstroms. So we're talking about very small length scales. So whether or not this is going to be of anything other than academic interest, it's TBD. But there's also the other issues. Additional physics needs to be included. You know, there's also physical viscosity and conductivity, which also smears the interface. There's adding in an energy equation, which I should tell you, the Madelung equation, the Madelung approach does not give guidance on how to do that, to have a third equation, which is an equation for the energy density. As far as I know, only the Wigner approach does that. And we'd like to finish the simulations of shock formation in a real plasma, QHD for the electrons and ion fluid model. And with that, here's some references and papers for those of you who are interested. And thank you very much for your time.
All right. Thanks very much, Frank, for a really fascinating talk. Floor is open for questions. And Paul Bellin's the first question.
Can you go back to the second last slide where you had that ME over MI?
Yes, sir.
Yeah. So if you look at that last equation with the ME over MI, there's a 1 over ME in front of it. So the
yes.
M's cancel and you're just left with an MI.
Yes.
You wind up with the electron pressure terms acting on the ions just the way the ion pressure
right.
does. So that would give you something like an ion acoustic wave.
Yes. Good point.
Have you considered that?
I have not. In fact, if I go back here, and I just apologize if I go, if I've got it included. That's a very good point. And yes, in fact, if I look at the let me go back. Sorry, I apologize for doing this. Yes, if I look at this is the dispersion relation associated with the shock. I look at that equation. There is an acoustic wave, and you're absolutely right. So there's going to be both ion acoustic wave and these electron oscillations also.
All right. Any other questions? Yeah.
Hi. Thanks for the fascinating talk. I was just wondering whether the quantum hydrodynamics equation has a sort of small Mach number, incompressible analog sort of limit, where actually you wouldn't need to know the energy equation or the equation of state, and whether that would be interesting, or maybe it's trivially not interesting.
You know, that actually is I had not thought of that. I wish I was there and we could talk. But if you can send me an email, I would love to talk to you more about that. That's a very interesting observation.
Sure.
Any other questions? Are there any questions from the virtual audience? Just go ahead and open your mic and shout out. Sounds like there's not. I'll ask maybe one last question.
Oh, sure, Richard.
Is it possible to account for spin? Can you actually formulate equations for spin up and spin down?
Yes.
I think relativity probably would be easy to incorporate, but what about spin?
Yes, you can do that. In fact, there's a student I'm working with at Oxford where we're incorporating spin into the QHD equations. That, you know, it's a very interesting point, Richard, because that idea is sorely lacking in the QHD literature. In other words, people just assume that you've done sort of spin averaging. But it would be really nice to actually have a formalism that incorporates spin in a natural way. And you can do that. You just identify, you just have to have an additional index, spin index. But yeah, that's something I think that definitely needs to be done.
Very good. So let's thank Frank again for a wonderful talk.
Thank you, everybody.